Hi everyone. Our goal in this class is to find the best optimization methods that can optimize complicated functions as quickly as possible. You can see that depending on what kind of assumptions we make about the functions, we might need different algorithms. Some functions are easy to optimize and some functions are difficult to optimize. Intuitively, we can think that if a function is smooth, doesn't change a lot, then it's easy to optimize. However, if a function at some unknown locations change very quickly, then that function might be difficult to optimize. For example, if the function looks like this, then basically we would need to do a brute force search in the domain of the function to find that location where the function value drops by a lot. This brute force search is very expensive, especially in high dimensions. One might also think, if the function is differentiable, then it must be smooth enough. We have the gradient that we can use for optimization, so the function must be easy or not too difficult to optimize. However, requesting only differentiability is not enough. Any continuous, but otherwise ugly, wiggly, non-differentiable function can be approximated with a smooth, differentiable function arbitrarily well. Here is an example. The blue function is continuous, but non-differentiable, and it can change very quickly. Still, even this function can arbitrarily well approximated with this red differentiable function. Both functions can change very quickly, and because of that, both the original blue function and its approximation, the red function, are difficult to optimize. Therefore, assuming differentiability only will not help us get reasonable properties such as good optimization rates. We need stronger conditions to get rid of difficult to optimize functions. One such condition that we often request is that the derivatives have to behave nicely. The derivatives shouldn't change too quickly. Formally, we will assume that the derivatives are Lipschitz continuous. We will call this property smoothness. Below, I'm listing 6 different function classes. They make different assumptions about the smoothness and convexity of the functions. We will see that simple gradient-based optimization methods can achieve different convergence rates in these function classes. Later, we will formally define these function classes. For now, I'm just listing them. We will discuss k times differentiable functions, beta smooth, k times differentiable functions, k times differentiable convex functions, beta smooth, k times differentiable convex functions, k times differentiable strongly convex functions, and beta smooth, k times differentiable strongly convex functions. First, we will discuss k times differentiable possibly non-convex functions. Then we will investigate another function class where the functions, in addition to being k times differentiable and possibly non-convex, are also beta smooth. So let CKQ denote the set of possibly non-convex functions that are defined on domain Q, and they are k times continuously differentiable on this n-dimensional domain. K times continuously differentiable means that the functions are k times differentiable, and after we differentiated them k times, the functions we get are still continuous. For example, as a special case, if a function is 1 times continuously differentiable, it means that the function is differentiable, its derivative exists, and this derivative is a continuous function. Some of the proofs we require that the function we get after calculating the derivatives k times is still a continuous function. That's why we will need the k times continuously differentiable condition. However, we are a bit lazy, so instead we will often just say that the functions are k times differentiable. Again, here we don't assume that the functions are convex. They can be non-convex too. In the next function family, we will assume that the functions are not just k times continuously differentiable, but they are also beta smooth. Formally, this function class consists of real-valued functions f that are defined on the domain Q. They are k times continuously differentiable. And for a given p integer, the pth derivatives are Lipschitz continuous with parameter beta. That is, the norm of the pth derivative of f at x minus the pth derivative of f at y is upper bounded with beta times the norm of x minus y for all x and y. When this property holds, we say that the pth derivative is beta Lipschitz continuous, or just beta Lipschitz. This function class is denoted by ckp beta q. Again, function f doesn't need to be convex in this function class. In the literature, there are many different notations for the derivatives of a function. Here, you can see 3 different versions that sometimes we use. The first derivative is also sometimes denoted with f prime. That's the gradient vector. The second derivative is sometimes denoted with f prime prime, and that's the Hessian matrix of function f. When the first derivative of f is Lipschitz continuous with parameter beta, that is, f is in this C11 beta function class, then we often just simply say the function f is beta smooth. Formally, it means that this inequality holds for all x and y. Here is an example. Let function f be defined as minus beta half times x transposed x. We can see that this function is not convex. However, the derivatives are Lipschitz continuous with parameter beta, so the function is beta smooth. When we make the assumption that the function is beta smooth, that is, the gradient of function f is Lipschitz continuous with parameter beta, then several important inequalities will hold. It will be a homework exercise to prove these inequalities. These inequalities are important because often we can use these inequalities to derive convergence rates of the algorithms. We can also observe that the beta smoothness provides interesting upper bounds for some of those terms that were lower bounded when we assumed convexity. For example, when function f is convex, then the gradients are monotone, so this term is non-negative, that is lower bounded by 0. Beta smoothness, however, implies that this term is also upper bounded by this expression. Similarly, when the function is convex, we know its Hessian is positive semi-definite, so it's lower bounded by 0. This property says that when the function is beta smooth, then the Hessian is also upper bounded by beta times the identity matrix. Finally, we know that when function f is convex, then it can be lower bounded with its first order Taylor series expression. This inequality says when the function f is beta smooth, then it can be upper bounded with this quadratic expression in y. This is the first order Taylor series approximation plus this extra quadratic term. Remember, when function f was convex, then f of y was lower bounded with this linear first order Taylor series expression. In this case, function f is upper bounded with this quadratic expression instead. Here is an important lemma about the second order characterization of smooth functions. Let function f be in the C21 beta function class. That is, we assume that function f is 2 times continuously differentiable and the first derivatives are Lipschitz continuous with parameter beta. We can prove that function f is a member of this C21 beta function class if and only if the Hessian matrix of function f can be upper bounded by beta times the identity matrix for any x. Equivalently, we can say that the operator norm of the Hessian matrix is upper bounded by beta. If you don't know what the operator norm of a matrix is, then please take a look at the matrix norms slide deck. The proof of this theorem will be posted in the appendix slide deck. The next theorem and its corollary are also very important. The theorem says that if function f is beta smooth, not necessarily convex, then the error of the first order Taylor series approximation can be upper bounded by this beta half times x minus y squared norm term. An important corollary of this theorem is that if this function f is beta smooth, not necessarily convex, then it can be both lower and upper bounded by a quadratic function at any point y. This implies that if a function cannot be both lower and upper bounded with quadratic functions, then this function cannot be beta smooth. The proof of this theorem is also in the appendix. Instead of assuming that the first derivative is Lipschitz continuous, we could also assume that the second derivative is Lipschitz continuous. Formally, for example, we could assume that the operator norm of the Hessian at x minus the Hessian at y is upper bounded by parameter m times the norm of x minus y. Then we could prove these inequalities here. The first inequality is bounding the error term of approximating the derivative of f with the first order Taylor series expression of this derivative, which is actually the second order derivative of f, that is the Hessian matrix of function f. The second inequality provides an upper bound for approximating function f with its second order Taylor series expression. We can observe that in this case, the error of this approximation is cubic instead of just being quadratic when we did the first order Taylor series approximation. There are many other important inequalities. I skip them for now, but you can study some of them in the slide deck. Here is another, maybe somewhat surprising result. We can prove that if function f is beta smooth, then the function beta half times the square norm of x minus f of x is a convex function. This statement would be trivial if we had assumed that minus f is convex, because then this expression is just the sum of two convex functions. But interestingly, this statement is also true even when the function minus f is not convex. The proof of this theorem is also in the appendix. It will be a homework exercise to prove that if we are given a twice differentiable function f, then the gradient of function f is beta Lipschitz continuous if and only if the Hessian matrix of function f can be upper bounded with beta times the identity matrix. This lemma can be used to check when a simple quadratic function has beta smoothness property. When the function is quadratic, then in this case, the Hessian of function f is just 2 times q. So whenever beta is at least as big as 2 times the largest eigenvalue of q, then this quadratic function f will have beta smoothness. So far, we discussed two function classes, the k times differentiable functions and the k times differentiable smooth functions. Now, we are going to study k times differentiable convex functions. This class will be denoted by fkq, where again, q is the domain of the functions. As a reminder, ckq denoted the set of k times continuously differentiable functions on domain q. Now, fkq will denote the set of functions which have domain q and which are k times continuously differentiable, and each function f in this set also has to be convex. That is, function f has to satisfy this inequality. It's very easy to see that this function set fkq is a convex cone. It means that if we choose two functions, f1 and f2 in this set, and alpha and beta are two non-negative numbers, then the linear combinations of f1 and f2 with these alpha and beta multipliers is also a member of fkq. That is, this function will be also k times differentiable and convex. The next important function class is the class of beta smooth, k times differentiable, and convex functions. This function class will be denoted by fkp beta q. fkp beta q contains those functions that are k times continuously differentiable, convex, and the piece derivatives are beta Lipschitz continuous, and the domain is set q. As a special case, f11 beta contains those functions that are continuously differentiable, convex, and their first derivative is beta Lipschitz continuous. There are many inequalities that can characterize this property. Here I'm just listing a few of them. You can prove that f is in this f11 beta function class if and only if these inequalities hold. The proofs of these inequalities can be found in the appendix. Here is one more inequality that characterizes this property. You can prove this inequality holds if and only if function f is in function class f11 beta. Here, theta has to be between 0 and 1, and this inequality is a generalization of the Jensen's inequality for beta smooth convex differentiable functions. When the function is twice differentiable, that is, its Hessian exists, then you can prove that the function is convex and beta smooth if and only if this Hessian is positive semi-definite and is also upper bounded by beta times the identity matrix. We already know if a function f is beta smooth, then there's a quadratic upper bound on the function, as you can see here in this inequality. We also know that convex functions always lie above their tangent lines. So this quadratic upper bound implies that beta smooth convex functions always lie above their tangent lines, but also below a parabola that passes through the point x and f of x. As a specific application, we can prove that although the absolute value function is convex, it's not beta smooth for any beta, since in x equals 0, we cannot upper bound the absolute value function with any quadratic function. As a final class of functions, let's define the class of strongly convex functions. We say that the function f is alpha strongly convex if this function gx, which is defined as f of x minus alpha half times the square norm of x, is convex. In other words, we have a function f, and even if we remove alpha half times the square norm of x, the remaining function is still convex. We already know that when a function is beta smooth, then it lies below a parabola passing through x and f of x. However, when a function is alpha strongly convex, then it lies above a parabola that passes through x and f of x. Because of this property, we like to say that strong convexity is a twin or opposite assumption to smoothness. On this slide, I'm listing several inequalities that hold for alpha strongly convex functions. When alpha equals 0, we just got back some standard properties of convex functions. These inequalities show how alpha strong convexity can make these inequalities sharper and as a result provide better bounds for us in proofs when we study the theoretical properties of certain optimization algorithms. Thanks for your attention for now. We are going to continue these discussions from here.